Well, welcome back, class. We're going to continue our discussion of classical physics. You remember in the first of these video lectures, we went back in time and we talked about some of the early scientists who helped us understand the world around us in what we now call classical physics. We talked about Aristotle and Copernicus and Kepler and Galileo, and we said the next person we'd talk about would be Newton. And so this section begins talking about Newton and his laws and the concept of gravity. But let me go back quickly and review what we covered in our first chapter, or review a couple of big questions that were addressed. One question about the world around us that mankind faced was, is the world flat or is it round? And of course, we now know it's spherical or round. And back in ancient days, the evidence really did point towards the Earth being spherical. After all, when the sailboats sailed away from a port, the last part of the boat that would be visible would be the top of the mast. Also, the positions of the stars, when observed by astronomers, depended upon the latitude of the observation. And also, when there was a lunar eclipse, the Earth's shadow on the moon was spherical. So really, that question wasn't so difficult to solve. The Earth is round, even though I guess sailors like Columbus and Magellan were worried about whether or not that was right. Probably the more vexing problem was the Earth the center of our solar system or of our universe, or was it the sun? And we talked about how Copernicus and Kepler and Galileo made observations and leading them to conclude that, in fact, the sun was the center of our solar system and that we on the Earth revolve around the sun. Now, one of the reasons why this was a little bit hard to accept is that if, in fact, the Earth is moving, if it's going around the sun, and if, in fact, it's rotating, why do we not feel that motion? Well, this was a question that perplexed Newton as well. And you remember the story is that he was thinking about this and an apple fell on his head and he then thought, aha, there is this force called gravity. But before getting to gravity, let's talk about Newton and his three laws of mechanics, or three laws of motion. Newton was an Englishman. He was a mathematician, an astronomer, a physicist. His most famous book was called Philosophia Naturalis Principia Mathematica, also just known as the Principia or Principia. In this book and in other writings, he essentially laid the foundation of classical physics. So let's begin by going over Newton's laws of motion. Three laws. The first law, an object will either remain at rest or continue to move at a constant speed and direction, or constant velocity, unless it is acted upon by a force. This is sometimes called the law of inertia, the tendency of an object to keep doing what it's doing, either to remain at rest, like I do a lot, or to keep moving at a constant velocity. In order to change the motion of an object, there has to be a force. A force has to be applied on that object. And here I show an image of maybe an ice skater skating along. In order for that ice skater to change its direction or to change its velocity, a force has to act upon that ice skater. Newton's second law is stated as, and this will seem complicated, the sum of the forces, capital F, on an object is equal to the mass, m, the mass of the object, multiplied by the acceleration, a, of the object. Okay, now that may sound complicated, but if you think of it in terms of an equation, the equation is F, force, equals mass, m, times acceleration, as shown to the right. Or as rearranged in the left side, it says that the acceleration experienced by an object is equal to the net force, F, applied to that object divided by its mass. Now, a simple way to understand this is to look at the very left where I show a man pushing two carts. One smaller cart and one larger cart. Now, common sense says that if the man applies the same force, F, to those two carts, the one that will move with the greatest acceleration would be the smaller cart. So that is essentially what this equation, F equals mass times acceleration, is all about. It means that if you apply the same force to a light or a heavy object, the light object will have a greater acceleration. Not so bad. Newton's third law, And this one you've probably heard of. For every action, there is an equal and opposite reaction. And a simple example of this, which many of you have experienced, is if you're on a skateboard and you push forward, the skateboard will fly the other way. For every action, there will be an equal and opposite reaction. Okay, so these are Newton's 3 fundamental laws of mechanics, and they led him further to understand this concept of gravity. The universal force of gravity. Gravity is an attractive force that exists between objects. Yes, you and I, or any two objects, have an attraction. Now, we may or may not feel that attraction, but there is an attraction between any two objects. In this slide, you see one object called M1 for mass 1 and another object called mass 2. And there will be an attraction between these two objects, these two spheres in this case. This attraction is due to a force called gravity. The gravitational force of attraction between two objects is directly proportional to the product of the masses of each of the object, that is mass 1 times mass 2, the product of their masses, and is inversely proportional to the distance squared, the distance d, as shown here, the distance squared between the center of the two objects. Now that's in words. In terms of an equation, that equation would be the attractive force due to gravity, F attraction, is equal to some constant, which we'll get back to, constant capital G, times the product of the mass of the two objects, M1 times M2, divided by the distance that separates those, d squared. So this is the equation for the attraction of gravity between any two objects. It's not so bad. The product of the masses divided by the separation distance squared, and then there is this proportionality constant called the gravitational constant. That's the capital G. Now this capital G has a value. Don't let it frighten you. It's shown here. It's a small number, 6.67 times 10 to the minus 11th. Newtons, that's what the N is for, meters squared divided by kilograms squared. So it's just a number. Don't worry so much about it. Just know that there are these constants that you'll run into every once in a while, and this is the universal gravitational constant. So we just learned that there is a force of attraction due to gravity between any two objects. Now you're thinking, I don't know if I feel that attraction, but you do feel the attraction between the Earth and yourself. And any object has the strongest attraction to the Earth. Why? Because the Earth is so massive. It is so massive that the gravitational attraction between us and any object in the Earth dominates our experience. Well, then let's look a little more at this attraction between us and the Earth. To do so, let's take the equation that we had a second ago. The force of attraction, the gravitational force of attraction, is equal to a gravitational constant G times the mass of the first body times the mass of the second body divided by the distance of separation squared. We also had, we learned a few lessons ago, Newton's second law says that a force is equal to a mass times an acceleration. Well, I put little subscripts here because now we'll be talking about the force due to gravity and the acceleration due to gravity, capital G. Instead of referring to this as the acceleration with a subscript G, another way we can write this is just by substituting the letter G, where G now is called the acceleration due to gravity. So this equation becomes this equation. The force of gravity is equal to mass times the acceleration due to gravity. Now, if we combine this equation and this equation, just combine them together, this is what scientists do and mathematicians do, they combine equations, we get this equation. And then if we refer to one of these masses as planet Earth, and we enter the mass of planet Earth, a value shown here, and the other we consider the mass of the object we're considering, which might be ourselves, and the distance is the distance between the center of planet Earth and ourselves standing on the surface of the planet, and we know that radius of the Earth, 6.4 times 10 to the 6 meters, okay? When we do this and we cancel things out, and this mass becoming the same number, the mass of either the object, which might be us, When we solve this equation, we get Earth's gravitational acceleration, little g, is equal to 9.8 meters per second squared. The value of Earth's gravitational acceleration. This gravitational constant applies not only to us and other objects on planet Earth, but it applies to the moon as well. This Earth's gravitational acceleration, little g, describes Earth's attractive gravitational force on any object. Now, notice that this value for little g, Earth's gravitational constant, is close to 10 meters per second, which makes it easy to remember. So if you want to remember 10 meters per second squared instead of 9.8 meters per second squared, that's okay. But it is the force that holds us to planet Earth, so that, as you see in our little diagram, we can all, no matter if we're at the South Pole, North Pole, we just stand on the Earth and it holds us in place. Okay, so we just talked about the influence of Earth on us. What about other planets that we might have an opportunity to stand upon, like the moon or Jupiter? What would be a person's weight? What would be the force of attraction between those bodies and a person, such as ourselves, if we were standing on the Earth, the moon, or Jupiter? And here I show you the relative size of the Earth, the moon, and Jupiter. Answering this question, what is a person's weight, or what is the force, the gravitational force, on Earth, the moon, and Jupiter? The more general equation that we've talked about is this equation, where this g is the universal gravitational constant, which has this particular value, 6.67 times 10 to the minus 11th Newton meter squared per kilogram squared. We then, in a couple of slides, we said that if we know the mass of the Earth and we know the radius of the Earth, we can simplify it for planet Earth to get this second equation. That is, force is equal to mass times the gravitational constant for Earth, little g. For a person who has a mass of about 63.5 kilograms, which happens to be about 140 pounds, that's what I used to weigh when I was in high school, and using the masses and the radius of planet Earth and the masses of Jupiter and the moon, we could calculate the following weights that you would experience, weights in terms of Newton, that you would experience on these different bodies. On Earth, our weight expressed in newtons, the force that is the force of attraction between the Earth and us, would happen to be 623 newtons. Now, I know you're used to thinking in terms of pounds, but bear with me for a second. This would be your weight as a force in newtons. On the moon, your weight would be 103 newtons, and Jupiter, 17,418 newtons. That is, these weights expressed in the units of force, you would weigh about 1/6 as much on the moon. You would be lighter on the moon because the gravitational attraction between you and the moon would be less, because the moon is less massive than the Earth. On the other hand, if you were to travel to Jupiter and try standing on Jupiter, you would experience a weight that is 28 times larger than your weight on planet Earth. Now, you'd have to develop some pretty strong leg muscles, like the Hulk, in order to walk around on Jupiter. Okay, we're going to pause again, have a little quiz, and then in the next video lesson, we're going to talk about falling bodies. Okay? Falling bodies. See you shortly.